Yeah, so it's a great pleasure to have Jeff Galkowski from University College London, who will speak on viscosity limits for zeroth order operators.
First of all, let me thank the organizers for inviting me to speak sort of in Montreal. It's too bad I can't be there, but next time. So I'm going to be talking about some work I've been doing with Zworski on viscosity limits for zeroth order operators. And before sort of going too far into it, I'm going to just give you some motivation. And all right, so this is a new technical level of challenge for Zoom, so I'm going to try to play you a video. We'll see how that works. So the motivation for this problem comes from actually some honest physical experiments where you put water in a tank and you make the density variable as you go vertically by sort of introducing salts. And what you can see here is that the waves are being, or the tank is being forced. Oh, okay, now this is not doing what I wanted to do. The tank is being forced from this side, right, with some kind of time harmonic solution. And okay, it's a little bit choppy, but maybe you can see that there's some kind of internal wave sort of here, right? Okay, so I don't know, maybe you can see it, maybe you can't. If not, then there's a link to the video on YouTube. And so you might wonder to yourself, what exactly is happening here? What's causing this sort of collection of energy at this interior trapezoid? And again, the experiment, this is an honest experiment where you arrange it so that the salinity of the solution is variable with vertical position, and then you just force with some harmonic forcing from the right. And so you wonder, you know, what's going on here? And so, okay, oh no, stuck. Okay, there we go. So you wonder what's going on here, and I'm not a fluid mechanicist, but people tell me that one approximation for this is this Boussinesq equation. And if you do numerical simulations with a similar problem, you indeed also see this this collection of energy at these interior trapezoids. And on the right, you can see how this collection of energy depends on sort of the angle and frequency of the wave, right? And okay, there's some degenerate thing that happens here when the parallelogram hits the corner, but at each energy you see some kind of accumulation, or sorry, at each angle and frequency you see this same phenomena going on. And this is with numerical solutions for the Boussinesq equation. And so, okay, you can sort of take this equation and diagonalize it into two pieces. And again, so I'm not an expert in this first part, but you end up with a problem that looks as follows. So you have this basically Schrodinger type equation with a right-hand side of harmonic forcing. And the sort of interesting thing is what happens is that you end up with something which is a zeroth order pseudodifferential operator, right? So it depends here on the density, right? The gravitational constant, this G, and then you have, your momentum in the vertical direction over the total momentum. So somehow by some linearization and reduction, you end up with an Schrodinger equation which involves a zeroth order pseudodifferential operator. And so now you wonder if you can see this, this phenomenon arising from the dynamics of this simplified model. And okay, so, oh, right. So I'm using a different tool to do the writing, so I'm not used to it. So hopefully I don't forget to remove things from the screen. But so again, you have this first zeroth order pseudodifferential operator, and you want to understand this accumulation of energy at some internal trajectory. And so one thing, of course, we like to do in sort of microlocal analysis, or just sort of geometric optics, is to understand this Hamiltonian flow. And if you stare at this Hamiltonian flow for a while, you'll realize that, okay, what can happen Well, what can happen is if I look at this piece, right, what can happen is if the left-hand piece vanishes, so if the movement sort of in the base is vanishing, then you can end up in a situation where if I draw the sort of xc direction, then I have just a pure radial expansion. In other words, the frequency, if I just have the C1 frequency and no other frequencies, then it's running off to infinity in the C1 direction. Right? So that's what will happen if this first part vanishes and you are in a position where C is just C1. And again, this energy will escape off to infinity. And so what you start to imagine is that, okay, well, what's this accumulation of energy? It's some kind of high frequency oscillation, exactly where you can get that, namely where the energy can run off to infinity. And I should point out that for those of you who are used to dealing with sort of the Laplacian or generally speaking, positive order elliptic operators, but this sort of doesn't happen there on a compact manifold because your energy surface is bounded, right? But now that we have a zeroth order operator, the energy surface is certainly not bounded, and so you, even though you're at some fixed energy, you can still escape in frequency to infinity. Okay, and all right, so now my computer's not cooperating. Okay, so what you start to imagine is that maybe there's some kind of source sink pair, so you can run in from infinity here and then go off towards positive infinity there. So I have some kind of source going on here and some kind of sink. And I'll be a bit more precise about this later, but now this problem is still a bit complicated, right? It has a boundary. And so we're going to remove the boundary. I mean, many of us have done work on boundaries and nobody really likes it. It's complicated and often distracting. I mean, sometimes, of course, it's very interesting, but in this case, we're going to see that it's distracting. Okay, so now we're going to remove the boundary and I'm going to sort of introduce you to a very simplified model. So I'm going to work on a smooth compact manifold, namely the n-dimensional torus. And I'm going to be thinking P is a self-adjoint zeroth order pseudodifferential operator. And so what does that in particular mean? Well, it means that the symbol will be some zeroth order homogeneous operator. And I'm going to be fixing my energy omega 0. This is the frequency of oscillation, right? Remember that the equation I was looking at was something like this. All right, something like this, some harmonic forcing. And so this omega 0 is precisely the frequency you're forced with. And I'm going to ask that, okay, I don't have sort of degeneracy on that energy surface. And again, I want to point out that since this is a zeroth order operator, this energy surface can go off to infinity. And now what I'm going to ask is precisely that the Hamiltonian flow for this modified vector field, so has a source sink structure sort of at infinity. So what do I mean by this, right? I mean that I'm going to take my energy surface, which of course is conic, all right? And so I'm going to quotient by the radial action, and I'm going to look at the vector field on the new object, right? So on this is something I'm going to call sigma. And okay, this scaling here is so that at sort of fiber infinity, you have a non-trivial vector field, right? I mean, remember that P is zeroth order, so HP is minus first order. So if you want something that extends nicely to infinity, then you should multiply by absolute value of psi, right? And I'm going to ask that this has some kind of source sink structure. So more precisely, I'm going to ask that it be more small. So what does that mean? That means that it should have a finite number of hyperbolic limit cycles, and every trajectory which is not one of these limit cycles should have a unique forward and backward limit that's one of these limit cycles, right? So this is sort of the nice stable model for hyperbolic dynamics. Okay, and all of this, remember, is happening at infinity somehow. Okay, so this is the setting I'm going to work in. Again, we've removed the boundary to simplify the problem, and I want to stress that it's crucial that this is a zeroth order operator. Okay, so now let's look at some examples, right? So again, on the torus, in this case, just the 2 torus, right? And so here's a simple example for you. You just take the momentum, so you know, momentum 2 over the absolute value of momentum and subtract simple cosine. And what you observe is that your sigma is the union of 2 tori, right? Actually, under this Morse-Smale assumption, it will always be the union of some number of tori. And what you end up with is you end up with these 2 tori, and your hyperbolic limit cycles are this guy, this guy, this guy, and this guy. Okay, and if you compute just, if you, and sorry, my omega 0 is 0 here, right? And so you can check that indeed at x1 equals pi over 2, you have this radial vector field in certain places in frequency. Okay, so this is one example, a simple example you can keep in mind. You can change that example slightly, right? And you can just change the sort of size of this cosine, and what happens then is your sigma, this quotient of your energy surface, the tori sort of join together in a different way, but the hyperbolic limit cycles are the same. Okay, so these are still exactly the same hyperbolic limit cycles. Okay, and so in either case, you have these nice attracting Lagrangians at x1 is either plus or minus pi over 2, and the sign of C1 should be fixed and C2 should be 0. So these are the sort of sinks of this flow. This is where you end up if you flow forward in time for long enough. Okay, and this structure turns out to have some nice consequences on the spectrum of P. So this theorem is due to first Colin de Verdiere and Saint-Raymond. Dyatlov, Zworski sort of brought it, well, that's how I learned about it. And then Colin de Verdiere proved this if you don't assume that there are no fixed points. And so what the theorem says is, okay, I work on the torus. This is really the 2 torus. And I ask that, and I ask that all of these assumptions are true. So again, a 0th order pseudodifferential operator, it should be self-adjoint, the differential shouldn't vanish, and I should have this Morse-Smale structure for the flow. And what you can see then is that near the energy 0 in this case, so omega 0 is 0 in this case, you have the following structure for the spectrum. It's absolutely continuous with possibly finitely many pure point spectrum embedded and no singular continuous spectrum. And okay, one way of proving such a thing is to find that you have a limiting absorption principle away from eigenvalues, right? So in particular, if you're away from an eigenvalue and you take this limiting absorption resolvent, you can see that it maps smooth functions to some kind of, okay, these are Lagrangian distributions associated to this attractive Lagrangian, but if you don't like those words, then you should just think that it's a map from C infinity to something slightly worse than h minus a half. So by relaxing the conditions on the space, as usual, you get some limiting absorption principle. And let me now, of course, draw you a picture, right? So this is saying, okay, I'm interested in a little neighborhood here of 0, right? Remember, I always have some omega 0, but one nice thing about 0th order pseudodifferential operators is a shift is sort of the same level as the actual operator itself, and so you can just shift and move things to 0. Okay, and so now what you see is, again, you have this small window minus delta to delta on which things are absolutely continuous, except you might have some eigenvalues. Okay, and so now you want to ask, what does this say about the actual dynamic? So I remember you have this problem that you want to solve here. You want to understand what happens with that problem. And again, this is a theorem due to Colin, Verdiere, Saint-Raymond, and Dyatlov, Zworski. And so what they ask is, okay, suppose you don't have omega 0 in the pure point spectrum. So this is not an eigenvalue of your problem. And you try to solve this forcing problem. Okay, and so what happens to you? Well, what happens is you get a solution that looks as follows. So the sort of biggest term in this expansion is this one here, right? So it's an oscillating factor, exactly e to the minus I omega 0 t times some u infinity. That u infinity is in this space of Lagrangian distributions. Okay, if you want, this is, you know, again, contained in h minus a half minus. And so that's the main term. In what sense is it main? Well, it's main in the sense that you have a piece which is just bounded in L2. So this is, you know, more regular, plus something whose singularities in h minus a half minus go to 0. So same regularity, but small. And so if you think about what that should mean, it means that when you see sort of high frequency oscillations, they're coming precisely from this first piece. Okay, and so let me go back to this example. Okay, I changed it ever so slightly in that now, instead of having dx2 over absolute value of d, I have this Japanese bracket, and that's just to make this, you know, easier to code up. And so we're going to look at actually the solution of this problem. So I don't know, hopefully this video is sort of working, but you start with, you force from 0 this, this problem with the f I described here. Okay, sorry, I have an eraser. So with this f, and you can see what happens. It accumulates at, well, what should happen? It should accumulate at pi over 2 and minus pi over 2 in terms of its oscillations. And you can really see this happening in these simulations, right? So they really accumulate at these attracting Lagrangians, and you can see this structure coming out. Okay, and this is actually, this video was done by Semyon Dyatlov. Okay, but it's really, you can see from the spectrum, and from this limiting absorption principle, how things are looking, right? They're mapping you into these attracting Lagrangians. Okay, so now, you know, we sort of have some basic understanding of the spectral theory of these zeroth order operators, and we know to some extent what effect this structure has on the dynamics, right? But of course, in real life, right, in real life, fluids are viscous, and our model had no viscosity. So what I'm going to think about for the rest of the talk is what happens to these problems, what happens to the spectral theory if we add a small viscosity, right? So that's this term here, this is my viscosity term, and nu is going to be some small, I don't know why I always spell viscosity wrong, but I do. Viscosity. So this is my viscosity term. And so we're going to be thinking about what happens when this viscosity is present but small, right? And actually some people in fluid mechanics have used this as a model for sort of modes which are appearing at some frequency, which is of course controlled by nu, right? I mean, it's unreasonable in real life to expect sort of frequency honestly to go off to infinity, and that's exactly because of things like damping, which is coming from this viscosity term. So what should happen is you get modes which are oscillating at some frequency, which is controlled by this nu. Okay, and so you want to know what's happening here. So let me now state the theorem. Okay, and so we're gonna, as before, assume that P has, again, it's a zeroth order pseudodifferential operator, should be self-adjoint. it should have this type of Morse-Smale structure. I mean, we can weaken that slightly. We just need it to have source sink structure, but it should have some hyperbolic structure with respect to the source and sink at fiber infinity. And we're going to have to ask that P be analytic near the cotangent bundle of the torus. And then what happens? Okay, so what happens is that there's a neighborhood of 0 so that the spectrum of this operator with viscosity converges to some discrete set. So okay, so I will put a picture up in a second, but I should say from the start, just for full honesty, it's not totally clear if there's a nice mathematical statement of what these points are saying. So you have this nice description of the spectrum of P plus I nu as I nu Laplacian as nu goes to 0, but it's not totally clear what effect these should have on the dynamics. Okay, but let me sort of now tell you what this theorem says, right? Again, under all the assumptions I've made about P, so it says this hyperbolic structure at 0th order, et cetera, et cetera. What it says is that you had your continuous spectrum, right? You had this continuous spectrum in minus delta to delta, possibly with some eigenvalues. And what this says is there's a neighborhood, right? There's a small neighborhood now of 0 in which you have some nice set of values. So these x's I've drawn here, where the spectrum of P plus I nu Laplacian accumulates as nu goes to 0. So this, of course, I should point out that P plus I nu Laplacian has a discrete spectrum on L2 because the Laplacian is elliptic and P is lower order. But now we're saying that we have some understanding of what happens as nu goes to 0. And what happens is that these eigenvalues sort of come in and they accumulate at these points. So these are, if you want, the spec of P plus I nu. And they come in as nu goes to 0 in this direction. And they accumulate here. And okay, I've drawn it this way, but one can see that in particular, if there are eigenvalues like this, then some of these eigenvalues of P plus I nu will come in and accumulate here. Okay, so now let me show you a video of what this looks like in some numerical situation. So let me start it over because I don't know how, probably should have slowed this down, but anyway, you can watch and you can see that the black dots are the P plus I nu, and the red, some of the red dots anyway, are this discrete set. So as nu goes to 0, you can really watch all of these things come up. And okay, so that unfortunately disappears at the end. But you can watch these things as nu is going to 0, and they run in from infinity and accumulate at these red dots. Okay, and so, okay, let me try to pause it there. Oh, no, I missed it. Let me try one more time. So let me try to pause it here at the end. All right, so you can see that very close to the end here, these black dots are very close, right? They're sort of accumulating like so. Okay, so that's what the sort of goal of our study was, is to understand this behavior as nu goes to 0, and in particular to see that there's some discrete set where these eigenvalues are accumulating. Okay, and again, I remind you, here's the theorem, right? It says, once again, that this discrete set, the spectrum of P plus I nu, converges as nu goes to 0 to some fixed discrete set, which depends only on the operator P and not on anything else, right? It's just depending on the operator P. And so
Jeff,
for those of you who...
Jeff, and what was the red region in the movie?
That's this R of P. I'll explain, of course, what it really is, but it's this R of P, right? So these red stars, at least the ones close to 0, are this R of P. This stuff, well, I'll try to say what that is later.
Okay.
Jeff, I have a question. So are these, so these are all now just resonances, or some could be eigenvalues at this point?
Okay, so the black ones are eigenvalues of p plus I new Laplacian.
Yeah.
At the moment, I haven't said anything about resonances, although of course you anticipate what these red stars really are. They're some kind of resonances.
Okay.
But for the moment, they're just, the red stars are this discrete set R of P. And I'm going to try to, I'll tell you what this R of P is, but it's going to be some kind of resonances. Does that answer the question?
Yeah.
Okay, and so as I was actually about to say, so for those of you who are sort of, who have thought about scattering theory, you might be thinking to yourself, well, this looks like some kind of meromorphic continuation of a resolvent through a continuous spectrum, and the poles of that meromorphic continuation are resonances, and indeed, that's exactly what's happening here. And I'm going to try to explain what that, how that works and what that looks like. Okay, so before I go too deep into how this actually works, let me review some other work in this direction. And so I pointed out at the beginning that the crucial feature here was this escape to fiber infinity. And you've seen now throughout the talk that I'm always making this assumption about the Morse-Smale flow. And that means exactly that you have these hyperbolic limits at infinity where things escape, right? And so one of the first places I'm aware of where this type of viscosity limit was explored is in work of Dyatlov Zworski on Ruel resonances. So what they did is they said, okay, let's take a vector field on some compact manifold which generates an Anosov flow. Now, okay, Anosov flow, it's sort of the nicest model of hyperbolic dynamics, and what it has is that, you know, things expand and contract extremely rapidly, and expansion and contraction, when you take a function and expand and contract it very rapidly, you get escape of frequency to infinity, and it happens very rapidly. So this is why somehow, if you think about the dynamics generated by an Anosov flow, it will have frequency escape to infinity very fast. And so what Dyatlov and Zworski did is they looked at x plus nu Laplacian m, right? And this adds, again, some kind of, if you want some kind of damping to the system, or in this case, you should think of it as actually some kind of random perturbation, a Brownian perturbation of this, this path. And what they show is that as nu goes to 0, if you look at the spectrum of this x plus nu Laplacian, you get convergence to Ruel resonances. So that's, again, some type of poles of a meromorphic continuation, either of a resolvent or some kind of zeta function. Okay, and there's some additional work by Drouot, which weakened how much sort of randomness you need. You only have to take sort of, rather than the whole Laplacian, you take only some directions. Okay, and you also have similar strong escape to infinity in some work of Franco, Losev, Nekrasov, and this was really just for the height function on the sphere and not from a sort of a microlocal perspective, but more recently by Deng Riviere, where they study general Morse-Smale functions and basically the gradient flow, right? So this Liouville vector field with the gradient of f is the generator of the gradient flow, and again, if you have the Morse-Smale condition, then your gradient flow will be hyperbolic, in particular Morse-Smale, and that causes rapid escape to frequency infinity. So when you add in this small perturbation, again, you get convergence of the eigenvalues to Ruel resonances. So these are both strong escape to infinity. Okay. What about something where there's sort of weak escape, right? Again, in the first two cases, right, these are sort of hyperbolic, which means rapid escape, sort of exponential escape to infinity. What about weak escape to infinity? So one place where we know that occurs is in just standard scattering theory. So scattering by, say, a compactly supported potential on Rn. And this is again due to Zworski. So he looks at scattering by a fixed compactly supported real valued potential, adds in this complex absorbing potential, right? So now you should think that this is a complex absorbing potential. So this is sort of a method people use to calculate resonances in quantum chemistry. And what Zworski shows is that, again, the eigenvalues of this operator, right? So now this whole operator is elliptic in some sort of global sense, right? It's not just elliptic at frequency infinity, but it's elliptic at physical infinity as well. And he shows that the eigenvalues of this operator converge to the resonances of the scattering problem. Okay, and so I want to pause and observe that, remember, in this Euclidean setting, so I forget that there's a potential for the moment, and I observe that, of course, the Hamiltonian flow is nothing but this guy, right? And so what happens is that as you go off to, you go towards infinity, right? Then you end up, if you sort of compactify things, you end up exactly with a radial type sink, right? Because as you go off to infinity, this is looking more and more like the radial direction. So if I just flow along this direction. But of course, it's happening only linearly in time. There's no exponential escape. Okay, and this is related to the fact, this reason that you need to do something like complex scaling here, and that uses some kind of analyticity, right? So in order to do complex scaling, you need analyticity near infinity. Okay, and this can be generalized, of course, now I've written over where that appears, to potentials which are exponentially decaying as long as you're only interested in resonances which are close to the real axis, sort of in a fixed depth into the complex plane. And again, this exponential decay is really crucial here because it's compensating. Notice I don't have any extra assumptions in the strong escape case. Here I have to either assume it's, say, compactly supported or exponentially decaying, and this is because I have this very slow escape to infinity. Okay, and so the place where this zeroth order viscosity limits fits in is we have weak escape to frequency infinity, right? And the reason we have weak escape to frequency infinity is because we have a zeroth order operator with some kind of radial source sink structure. If you want to sort of get from between these two things, then, okay, if you take the Fourier, you sort of forget that there are high frequencies in the scattering problem, and you take the Fourier transform, then you can put this one into this picture, okay? So if you sort of conjugate by the Fourier transform and forget that there were high frequencies here, you end up in this weak escape to infinity structure. Okay, so now I want to try to explain how you can really explore these viscosity limits, and it will involve the use of some kind of analytic structure and the meromorphic continuation of a resolvent. So how does one typically do this? So the sort of robust way of doing this is to find spaces on which your operator P is Fredholm for energies near zero, right? So again, I'm asking that P minus omega Fredholm sort of for omega small. And again, I want to stress that here the energy honestly matters, right? Again, if you're talking about the Laplacian, then, so in contrast, the Laplacian, when I subtract an energy, right, this energy doesn't matter when it comes to Fredholm properties, right? It's so much smaller than the Laplacian, and say on a compact manifold, that this thing cannot change Fredholm properties. And so when I talk about the Fredholm property of my operator, I'm really talking only about the Fredholm properties of the Laplacian, and that makes you happy. Now you have an operator P, which is 0th order, and this omega is the same size as P. So when I vary omega, it really can change the Fredholm properties of my operator P. And so again, the sort of one robust strategy for doing meromorphic continuations is to find spaces on which you have the Fredholm property for omega near 0. And so that's what we're going to try to do. Oh no. Okay, so and then you apply the analytic Fredholm theorem, right? And that will give you meromorphy of the resolvent. Okay, so once you have sort of meromorphy of the resolvent for P, you need to know that, of course, this P nu should act nicely on these spaces. I'm not going to say exactly what that means right now, but it should act nicely on these spaces. And this is usually easy because the Laplacian is elliptic, right? And that helps you. Okay, the thing that's maybe less easy is that not only should this thing act nicely on these spaces, but it should do so uniformly in nu positive. If you want to understand, you know, so the way I want to think about this is I want to think about comparing P plus I nu Laplacian minus omega inverse in some sense to P minus omega inverse on some spaces. So this resolvent here, which makes sense, right? This one makes sense on L2. I need to make sense of it in some uniform way as nu goes to 0 on these nu spaces. And if I can do that, then often I can see that these things approach one another in an appropriate sense. Okay, and that's the last step, right? So I want to show that the resolvent of this P nu converges in some sense to that of P. Okay, so sorry. So that's the strategy. Try to find spaces on which P is Fredholm. This is sort of a robust tool for doing meromorphic continuations. Apply the analytic Fredholm theorem and get some uniform understanding of P nu as nu goes to 0. Okay, so what are these R of P then, right? This, remember we had the set R of P where the spec of P plus I nu goes to R of P. Well, this R of P, these guys are nothing but the poles of P minus omega inverse on my nu spaces. All right, on my nu spaces. That's okay. In other words, there's some kind of resonances for P. Right. So this is just like, again, if you're familiar with sort of standard scattering theory, right? You have to weaken the spaces on which your operator acts in order to get this Fredholm type property, or and get a meromorphic continuation. Okay, so let's have a look again at an example, right? So if there's time at the end, I will talk about the general theory, but I want to sort of give you an idea of what's happening by looking at a simple, in this case, one-dimensional example. All right, so I'm just taking P to be sine of X. You should think that this is, you know, sine of X times 1 plus or 1 minus V. It's just that I write it this way so that it's actually self-adjoint, right? And V, in fact, is extremely small, right? I'm going to have it be exponentially decaying. And I'll explain what's going on there in a moment, right? But this is, of course, a 0th order pseudodifferential operator. It's almost, I mean, up to this exponentially decaying thing, it's almost just sine of X, right? So a multiplication operator. And the reason that I took this very particular V is because an undergraduate at Berkeley actually, you know, computed and saw that P actually has an embedded eigenvalue. So you really can have embedded eigenvalues at 0, right? And you can, so this is what the spectrum of P looks like, right? So this is that picture. I used to have this, this line here in orange, and I think in orange, anyway. and this was a black X, right? So you really do have this, this situation where you have an eigenvalue inside the continuous spectrum, and that's what I've drawn here. And on the right, I've put the eigenvalues of p plus I nu Laplacian for several values of nu, where, okay, so blue is the smallest nu and green is the biggest nu. Okay, and let's zoom in a little bit. So okay, we have all of this sort of spectrum going on out here, but that's outside of the set really where I have this meromorphic continuation. That's somehow what's happening there is that's basically the boundary of that set. Okay, so we're going to zoom in and make sure we're inside the compact set. And so let's again look a little closer, right? So what's happening here is the biggest nu, here's the smallest nu. So these guys are accumulating to some resonance in the lower half plane. And here's that eigenvalue, right? Here's that eigenvalue. And the reason you only see one dot is because they're all on top of each other, right? So this pole is really just sitting there somehow. Okay, so that's what happens in this example. And let me try to explain what the spaces look like. So here I have the same operator. I'm going to write now the symbol. Well, the symbol, remember, v is, you know, super exponentially decaying. So certainly it doesn't show up in the symbol. So the symbol of p is nothing but 2 sine of x. And I can compute the Hamiltonian vector field, of course. It's just minus 2 cosine of x dc, right? And so, okay, that's what you have. And so one way of seeing this escape to infinity is that you can find what's called an escape function, this g, so that when you flow along g, this is just positive, and this is on p equals 0, right? And so, you know, one can usually locally do this, but the thing which tells you things are really going off to infinity is that I'm asking for a global escape function in this case. Okay, so you can check if you take g as I put it here, then you will have this property, right? And I'll compute the Hamiltonian vector field in a second. But here I have a global escape function for this problem. And what's the idea when there's rapid escape to infinity? Well, the idea is that you conjugate by e to the rg, or e to the r times, you know, the quantization of g. And if g is like I described above, then this is a nice symbol, right? If g has this logarithmic growth in xi, then that will be a nice symbol. Okay, so let's see what happens when we do that to our operator. All right, so we conjugate p by e to the rg. E to the rg is nothing but, you know, this d to the 2r cosine of x, or maybe minus g. And what happens is I get p minus ir hpg, or sorry, h sigma of p, I should have written here. Okay, and what's that? Well, that is just 4 cosine squared of x times d inverse. Okay, so this is good in some sense, right? Because here I have something with a fixed sign, right? I have a fixed sign imaginary part, and so you can imagine that this is enough to get some kind of ellipticity for this problem, because when I have my real thing is 0, I have this imaginary part to save me. Okay, well, that's kind of works for real energies, and indeed that's essentially what happens in these proofs of the limiting absorption principle, is that this is enough to get you ellipticity. But if you're interested in omegas which have an honest complex part, right, if I subtract an omega here, this guy is much bigger than the ellipticity. Okay, and so the reason for this is precisely because I have slow escape to infinity. If instead I had rapid escape to infinity, then I would be sort of able to get the same type of expression, except for now I would have no d inverse here. I would just have a 1, and that would be enough to control this minus omega. But because we have slow escape to infinity, this is now a D inverse, and so it doesn't beat the imaginary part of any fixed omega. Okay, so what's the fix? And sorry, by the way, I should point out that this is essentially how you prove these so-called radial point estimates due to Melrose, Vaschi, and so on. Is you conjugate precisely by such a thing. Okay, so what do we want to do? Well, we want to sort of soup up G. We want to make it bigger, right? We want to make it sort of so that when I conjugate by e to the RG, I get something which can compete with omega. So what do? Well, I just, instead of taking log of xi, I put just xi, or maybe absolute value of xi, but whatever. So that's what I do. And what's my issue? Well, the good thing is that HPG is now the same size as omega. So if I multiply an R here, right? If I multiply an R in front of HPG, then that can really control any fixed omega. The bad thing is that e to the g is most definitely not a symbol, right? This is an exponentially growing or decaying thing, and it's definitely not a symbol. Okay, and so that's a serious problem, right? You cannot form this operator really very easily, and this is where the analyticity comes in. If you want to be morally at least conjugating by e to the g with g this linearly growing object, then you need some analyticity running around. Okay, so in general what you do is you make complex deformations of phase space to make this work. So again, I will talk about that at the end if there's time, but here we're lucky mathematicians and we can do complex scaling. Okay, and this problem is set up precisely so that you can do complex scaling, and so that's what I'm going to explain on the next slide. Okay, so again, I look at the same problem here, and I want to understand how these spaces work, right? How do these spaces work? So I'm going to use the method of complex scaling in this case, and I'll explain how that relates to the deformations in a moment. So what that means is I'm going to move from the torus, which is just x, to some complex version of the torus, some shifted version of the torus given by some small shift theta times a function of x. Right, and what that really means is I'm going to send p to p sub theta, where p sub theta is basically the restriction of p as a an operator with analytic coefficients to this new contour gamma of theta, which is the shifted version of the torus. Right, so if u is analytic, again, you can take pu, you can analytically continue it and restrict to gamma of theta. And that should be the same as what happens if I restrict u to gamma of theta and apply this p theta. That's how you can define p theta. Okay, and you can check for yourself just by making a change of variables in this case that what happens is p theta is very close to p minus I theta hpg g tilde xi. Right, so somehow what's happening is that g on my previous slide, so this g I had on my previous slide is g tilde xi. So in other words, doing complex scaling is like having a weight function which is linear in xi, an escape function which is linear in xi. Okay, and again, if I take the g tilde, the g that I had before, so g, remember, was minus 2 cosine x xi, then what I end up with is this guy. All right, and this minus theta cosine squared is in particular positive when p is 0, because when p is 0, sine is 0. So this guy can beat, this one beats a shift, a small shift, all right, omega. Okay, and so now you have an honestly elliptic problem, and you get the Fredholm property, right? So p theta minus omega is Fredholm as long as imaginary part, sorry, there should be an omega here, is small enough, right? Okay. And also another crucial thing, so that's enough to get you this Fredholm property of P, right? I found these spaces by deforming the contour. A crucial thing about this viscosity term is it has the same sign, right? It has the same sign of as this this shift I've made here, right? So that means that when I send nu to 0, nothing bad happens to me because this I nu Laplacian is just helping me even more, and that's what allows me to understand things uniformly as nu goes to 0. Okay, so let me again show you some pictures, and hopefully this will, yes, okay. So now I'm looking at a slightly more complicated problem, a two-dimensional problem, right? So you'll see that this part here is the same as the one-dimensional problem I had before. This could be really a function of sorry, this should be a 1. Well, it could be anything, but anyway. So I add some other potential here, and now my 0th order operator is looking like dx2 over Japanese bracket of d, right? So now what happens is, of course, you can, the way I've set this up, you can separate variables, and that lets you do nice numerics. So now let's look at these pictures again. So these are similar pictures to what I was showing you before. And on the left, what I've done is I've put the poles, so these blue guys are poles of the meromorphic continuation, okay, with some fixed positive theta. And the other ones are theta 0, but nu going to 0. And again, with the light blue triangles, the largest nu, and the red ones, the smallest nu. All right, so you can see what happens is that, again, these dots are accumulating at points, so here, 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 and so on, in the poles of this meromorphic continuation. And if you plot a slightly different picture, which is that I change now theta and leave nu equals 0, you can see that what happens is you open up bigger, so when nu is small, I get sort of this region as my u, or sorry, when theta is small. And as I increase theta, I get bigger and bigger regions. So here I've uncovered a whole new layer of resonances, and you can keep doing this. Okay, now there's an interesting thing going on here at the edges, right? And that's precisely where this, this condition on more smell, this is where it fails, right? So if you take the energies at these endpoints, then this more smell type condition will fail. And that's why you don't get a meromorphic continuation there. Okay, so, okay, I did that. Yeah. So I remind you of the video, right? So you get this accumulation at these red dots, which now we know are just resonances of some operator on these complex scaled spaces. As nu goes to 0, you get this accumulation. Okay, so in the last, I guess, do I have 5 minutes? What's the convention here?
Yeah, sure.
Okay.
Yeah.
So in the last 5 minutes, let me sort of indicate at least what you want to do if you don't have a linear escape function. So the crucial thing that let us do complex scaling is that I had a global escape function which was linear in Xi. If you don't have that, you're forced to deal with much more complicated escape functions, and you cannot use the method of complex scaling. So what you want to do is you want to conjugate by e to the g of xd for some g now in S1. And again, this of course makes no sense, right? Because g is real. This is an exponentially growing thing in Xi. I'm basically flowing the heat equation backwards. That's no good. Okay, so what you want to do is you first of all need to use some analyticity, and second of all, you want to do this on the FBI transform side. Okay, so what that means is we're going to build on some work that goes back quite a while now. Boutet de Montville Sjöstrand, Helfer Sjöstrand, Martinez, Nakamura, they all introduced various notions of FBI transforms and deformations thereof, or weighted spaces. And they sort of built some tools which let you handle this type of thing. I mean, and in particular, the main inspiration for this type of FBI transform was due to Sjöstrand in '96, where he constructed an FBI transform in the semi-classical setting, which lets you handle sort of compactly supported, if you want things that are like compactly supported G's, but now where you have H's running around, so they're still big. Okay, so I don't worry too much about what that is, but the point is that we need to find an FBI transform which lets you deal with weights that are growing linearly in Xi. And that imposes some analyticity restrictions. And it allows you in particular to measure microlocal analyticity if you want the analytic wavefront set using sort of spaces on the FBI transform side. And this has applications, for example, to analytic hypoellipticity of Keldysh type operators, which can tell you, for instance, that some resonance states in general relativity are analytic rather than smooth, which is sort of nice. Okay, so what does this FBI transform look like? Right, so it looks like as follows. Okay, so there's a couple of things I want you to observe from this slide. So I'm going to give you the integral kernel of the FBI transform, and it's going to look like this, right? It's going to look like the usual FBI transform. Remember, the usual FBI transform looks like x minus y c minus x minus y squared. This is one version of it. Okay, so there's a couple of things which change. I need to put a xi here, and that's to allow me to handle things uniformly as xi goes to infinity. Right, so I'm going to do that. And I'm also going to insist that the entire kernel be analytic. So on Rn, that's of course very easy. This is analytic, just like that. But if you want to do this on a manifold, then you have to sort of fix things, right? So you have to take this kernel, which looks like this guy near the diagonal, cut it off, and then correct it by something which makes it analytic. Okay, and that's because I really need to be able to handle things. I need to be able to understand analyticity. I need to have when I need to know that this behaves well under sort of deformations in the complex. Okay, and if you want to do this on the torus, you can write one down explicitly, right? And it just amounts to summing the one on Rn over the lattice. Okay, and so what you end up doing is you take this FBI transform T. You have to understand that it has nice properties. You can invert it and so on. And you want to deform the sort of outgoing variables of this FBI transform into the complex, into this this now R-symplectic I-Lagrangian manifold. So this lambda is the replacement for T star M. Okay, so you just take TU, and you now notice that TU is analytic in X and Xi, and so you can restrict this to lambda, provided that lambda is reasonably close to the real or to the reals, right? And so this is now the type of thing you want to make assumptions about. You want to make assumptions that this TU restricted to lambda is in L2, okay, up to some weights, which I'm not going to talk about. Okay, so this is my lambda. And again, as I said, I want to take T lambda, which is this FBI transform applied to U, restricted to lambda. And I'm going to define spaces based on this FBI transform, namely that T lambda U should be in L2. And if you do that, okay, with some weight, then the crucial fact is that when you take inner products of P, U, and V in this H lambda space, this is a nice Hilbert space, then this is almost the same as applying the symbol of multiplying T lambda U by the symbol of P minus I theta HPG. So you get precisely this thing you expected from, this was sort of morally what happens when you conjugate by e to the RG, P e to the minus RG. Or maybe I've messed up the signs, but this is morally what happens. And in particular, it has a good imaginary sign provided that HPG is a good escape function, right? It has the fixed sign, and so it can give you the Fredholm property. Okay, and so I will stop there, and thank you for your attention.
Thank you very much, Jeff. So any questions or comments?
Yeah, so I have a question. So in the viscosity case, in the viscosity case, and can you say anything about the sort of generalized eigenfunctions, or?
I mean, you can say, for instance, that they are analytic, and I mean, they're in these spaces. It depends what you want to know. I mean,
no, I mean, I want to know about the the asymptotic structure, like the structure.
Yeah, so you can show that at least they converge in some sense to the resonance states of the sort of deformed this operator on the complex, but then you ask the question, what do those look like?
Yeah, exactly. Yeah,
and there's no asymptotic parameter anymore. I mean, you can probably, I think you can say, for instance, that they they have nice analytic microlocal structure with respect to these attracting Lagrangians, but maybe that's about it. I don't know much else.
Okay.
Other questions?
Yeah.
Nilama.
Yeah, thanks, Jeff. That was really great. So I have a follow-up question. I guess it's very similar to what John asked. My student and I have been trying to compute both the long-term evolution of the problem as well as some of the eigenfunctions. But when you're computing on the torus, the strategy that we're using is a spectral one. So you can split things into different directions and just compute. The problem with anything that we're doing computationally is, of course, that you can only track a finite number of Fourier modes, right? So we are seeing convergence when you take the viscosity to 0 of the computed eigenfunctions. What I'm hesitant, or what I'd like some help with, is just because we're seeing convergence is not enough. What do you have a sense of what the smoothness of the eigenfunction should be when it's when the viscosity has really gone down to 0? Because you guys are working with these strange spaces, right? So
Yeah, so I mean,
are the eigenfunctions for the embedded eigenvalues analytic? Is that?
For the embedded eigenvalues, they're analytic.
Okay. Okay.
But for the resonance states, they're not even functions.
Right. So, and that we actually see in a weird way. So what we did was we computed the evolution problem up to large times. And then we looked at the Fourier modes and we sort of computed the energy content that we see up to those Fourier modes. And then we changed the time. So we can see that as you increase time, the long-term behavior is not even an L2, right? So it's right. Weaker than H minus a half. That you can see. But we're interested in what happens with those eigenvalues for the viscosity operator, which happen to be going up towards an embedded eigenvalue. So we wanted to understand if we were doing that right.
Yeah, so I mean,
so those are analytic, eh?
The ones which are embedded should be analytic, yes. The ones which are below the complex are, hyperfunctions.
Right.
Yeah.
Right.
Or sorry, below the real axis.
Right. Okay, great, thank you.
Dima?
Jeff, in the physics experiment you showed with the fluid, the oscillations seem to localize near some kind of orbit, yes. Which reminds you of eigenfunction localization near periodic orbits. but it's probably something different. So is there, could you comment on what, is there some, is it a periodic orbit of something, or?
Well, it's precisely these hyperbolic orbits. I mean, okay, you know, you have a boundary, so things are different, but if you, at least if you delete the boundary, it's precisely these hyperbolic orbits here.
Yeah, okay. But on the boundary, will you have like angle of incidence equals angle of reflection in this situation, or something a little bit different?
I believe it's, you know, you can compute it, right? I mean, it's the usual thing where the, you know, when you hit the boundary, your tangent frequency is fixed, but your normal variable frequency can change. So whatever that means about the trajectory is what should happen.
All right. Thank you.
Some more questions? So if there are no more questions, so let's thank Jeff again for a very interesting talk. And so see you next week at the seminar.